So, hello everyone. This is E698G. This is our first lecture. Now, the title of the course is Circuit Design for Phase and Frequency Synthesis. So, what does synthesis mean? To derive. So, synthesis basically means to generate or to create something, right? So, synthesis now means to generate. So everyone understands what is meant by a frequency, right? Anytime you have an oscillation, there will be an associated period and you can calculate the frequency with it. And phase, right now, you can think of this as being equivalent to delay. There is a small difference between phase and delay. We'll see about its relationship in this course. But overall, this course is about circuits that are used to generate frequencies as well as delays. Now, commonly, when you think of an analog circuit, what circuit comes to your mind? If I say analog circuit, what is the first circuit that comes to your mind? Yeah, some sort of an amplifier, right? So when we usually think of analog circuits, we think of circuits that operate on some sensitive signal. The signal itself could be either in voltage domain or it could be a current signal. Now, in this course, we are more interested in the time domain information of the signal. Okay. Now, of course, the signal is complete when you have both the time domain as well as the amplitude domain information. Both of them are related also. But you will see that there are certain parameters that are used for quantifying the properties associated with the time domain of a signal. And we are going to be dealing with circuits that deal with these parameters. This is coming. So, the first and foremost, the most important signal where the time domain information is relevant is a clock signal. And I'm sure everyone is familiar with a clock signal. So a clock is nothing but a periodic signal. Now, this could be a square wave. It could be a sinusoid. Or it could be any other waveform that is periodic, such as a triangular wave or a periodic exponential waveform, etc. Right? But you will see that in most cases, we deal with clocks that are either a square wave or a sine wave, especially when it comes to circuit design. So now let me motivate you as to why we should pay so much attention to time domain circuits, especially that deal with clocks. So first I will show you the layout of a processor. Now this is an i7 processor from Intel. So basically a processor that you will find in your laptops. And here they have shown you how it is divided into 6 cores. They have a shared level 3 cache memory. Then there is a memory controller at the bottom, and there are some peripheral functionalities here at the top. So now, when you are running an operation on your laptop, such as playing a movie, we know that all of these logic gates involved in these cores as well as the memory are going to switch, correct? And we want to be able to sequence these events correctly for that operation to be run correctly. Now, for this, we synchronize all these operations to a clock edge. So the first major application of a clock signal is synchronization. Now, of course, it is not necessary that this entire block is going to be running at a single clock. You could have a clock and it's divided down frequencies, or you could have multiple clocks and the associated divided down frequencies. So when I say divided down, for example, let's say I have 100 megahertz, it's divide by 2 is very easy to generate. So if you have 100 megahertz, it's very easy to generate a 50 megahertz, 25 megahertz, etc. from it. Okay. So now let me show you the layout of another processor. This is also from Intel. And what I like about this layout is that they have beautifully shown how different parts of this processor are being serviced by different clocks. For example, you have these pink regions, which are basically controlled by this core clock. Similarly, you have gray regions, which are controlled by an uncore clock. And you have IO clocks that are clocking regions around here. Okay. They have also shown the placement of clock generation as well as delay generation circuits in this figure. For example, can you see the term PLL here? So PLL stands for, does anybody know the full form? Phase lock loop. So this is phase lock loop. Similarly, you can see another term DLL here. So DLL. And this stands for delay lock loop. So a PLL is a circuit that can generate clocks of different frequencies, and a DLL is a circuit that can generate stable delay. So what I mean by stable delay is that even if there is a temperature variation or a voltage variation or some variations in the process corner during fabrication of the IC, this delay will be stable, right? So we say that the delay is stable across process, voltage, or temperature, PVT variations. So looking at this figure, can you tell me the number of PLLs in it? So you will have to sum up all the IO PLLs, filter PLLs, uncore PLLs, and core PLLs. What is the total number of PLLs here? $15? 17. Okay, let's count together. How many IO PLLs are here? So 1, 2, 3, 4, 5, 6, right? Let's look at the filter PLL. So 7, then uncore PLL, which is yellow color, so 8. And then we have the core PLLs. So 9, 10, 11, 12, 13, 14, 15, 16. 16 PLLs. So we have 16 PLLs here. What about the number of delay lock loops? Eight? Yeah. So these are like typical numbers. If you pick up any system on chip, an SoC, either a processor in a mobile phone or that of a laptop, you will easily find more than 15 phase lock loops in that circuit. Okay. So what comment can you make about the clock frequencies in a laptop processor now? What is the typical frequency that you see? 2.3 gigahertz. Any other numbers? 3.4 gigahertz. So all these numbers are in the range. So I have again picked up another table from Intel's website. So let's focus on this portion. Okay, so these are the typical nominal frequencies of the core clock. And you can see that this varies between roughly 2.2 gigahertz to 3.5 gigahertz. Now, most of the processors these days will have an option for overclocking. That is, under specific conditions, for certain special operations, you make the clock go faster. So this you cannot apply for the entire processor, but under certain specific conditions, depending on the voltage, temperature, etc., you have to take a call on this. And that frequency, you can see, can go up to 5.8 gigahertz, right? So the frequencies are now within the range of 2.2 to roughly 6 gigahertz. And you can expect that these frequencies will only increase in the future. Because faster your core clock, the faster your laptop is. And we all want fast laptops, right? So the generation of these high clock frequencies, as well as the distribution of these clocks across the die to various portions within the die, both of these are very interesting design problems. Okay, so this is our first application. Now, let's look at the second application. Can you guess what this should be? What is the second major area where you see clock signals? So this is related to up and down conversion within a transmitter or a receiver. So these operations routinely happen in your mobile phone, in your laptops, etc., because they all have a transmitter as well as a receiver. So now I'm going to take a very simplified receiver architecture. And then we'll see where the clock is coming into picture. Okay, so first we have an antenna. So this antenna will receive RF signals. And let me roughly sketch how the spectrum is going to look like. So let's say all this information is around a carrier FC. So then my spectrum is going to look like this. So I've drawn a two-sided spectrum. Okay. So now what is the first component in the receiver chain after the antenna? LN. So the signals that are received by the antenna is very weak and we want to amplify them, but the signals are so weak that the amplifier's noise itself could corrupt it. So we have to use a low noise amplifier, which in short is called as the LNA. Okay, so the signal at the output of the LNA is still at RF frequency. What should be the next component? So this has to be a mixer. So our aim now is to bring the information around this carrier frequency to baseband, that is around DC. So what a mixer does is, it is going to multiply this RF signal with a clock signal. And what should be the frequency of that clock? It has to be FC. So what we'll have here is some sort of clock, let's say a cos signal, cos 2 pi FC of t. So its spectrum is going to look like this. So we get minus FC and plus FC, right? So now we are multiplying two signals in time domain. Therefore, in frequency domain, we need to convolve these two spectrums. So I will leave the actual convolution process to you to try out. But can you tell me what the output will look like after this? Where will it shift? So you will find that at 0, you will have both of these appearing. So you have your baseband signal here. Then you will also have signal information at 2FC and minus 2FC. Okay. But the information that we need is at baseband. We don't want these two portions within the spectrum. So what should be the next block? Yeah. So we filter it using a low pass filter. And once this is done, we have the information which can then be digitized using the ADC. So then we'll have digital information. We have learned all about digital in E619 and E370. Okay. So now let's focus on this clock 2 pi FC of t, right? So this clock is going to be generated from a local oscillator, usually abbreviated as LO. And this LO will be implemented using a phase lock loop. Okay. Now let's look at some numbers also. Let's say you are dealing with a Bluetooth receiver. So in that case, what would be the value of FC? Any guesses? Yeah. So this is at 2.4 gigahertz. What if this is a Wi-Fi signal? So this is again 2.4 gigahertz. And now we also have a 5 gigahertz signal. Yeah. So the carrier frequency, the value of FC is going to be 2.4 gigahertz or 5 gigahertz. So now let's take a radio, like FM channel. So let's say we are looking at Red FM 93.5. So then what would be the FC value, carrier frequency value? 93.5, what is the unit? Megahertz. Right? So these are some of the typical carrier frequencies that you will see. And you can imagine, right? The specifications on a clock used for these down conversion would be very different from the specification of a clock used for synchronization in a processor. The accuracy of this clock has to be exact. For example, let's say instead of tuning to 93.5, I tune to a slightly different frequency, 93.3, right? Then I will be listening to noise and not this particular channel. And if I tune it slightly away, I will be listening to a totally different channel. Therefore, for this down conversion algorithm to work, the carrier frequency in the radio station, in the transmitter within the radio station, and the carrier frequency within the receiver on our mobile phone, both of them has to exactly match, right? So can you feel the gravity of this problem? Yeah. So again, designing LOs, the local oscillators for up and down conversion, is again a very interesting problem. So now let me give you a brief look at what the other applications are. So like I mentioned, we have synchronization and up and down conversion. So clock signals are also used in serializer and deserializers. It's for short called as SerDes. This basically is related to wireline communications. It is used in radars. Time information is relevant in radars as well. Then it is also used in time to digital converters, digital to time converters, etc. So this time to digital converter and digital to time converter, you can think of it as ADC and DAC. Those terms you might be more familiar with, right? So there we digitize the amplitude information. Here we are going to digitize the time information. Okay. So this and many more applications are there. So now in this course, you will learn how to analyze and design delay lines. Then we will put this delay lines into a negative feedback. So that will give us a delay lock loop. So again, you will learn how to do a delay lock loop. Then we will do small signal analysis on this delay lock loop. So now you're familiar with one style of small signal analysis. Now here, it's again similar methods, but the small signal is now a time or a phase signal. That is why we are going to do small signal analysis in phase domain. Similarly, we'll deal with noise in time domain. And finally, we'll do oscillators, and we'll put this oscillator with a negative feedback, and that will give us phase lock loops. So this is the overall contents of this course. And at the end of this course, you will learn how to use feedback in time domain circuits, and you will learn how to analyze these circuits, and you will be in a position to design both delay lock loops and phase lock loops. So we have two teaching assistants for this course, Chandra Prakash Verma and Ruji Verma. And this is the overall grading for this course. So mini quizzes, if we conduct n mini quizzes, we'll choose the best of n-2 for each student. So if we have 6 mini quizzes for each student, we'll pick the best 4 mini quizzes. So what this means is that if you miss one mini quiz, there is no question of makeup because it is not going to affect your grade. But if you miss more than 2 mini quizzes and you want a makeup, you will have to provide valid reasons for all the mini quizzes that you have missed. Okay. Mid-sem is 25%, end-sem is 30%, and projects are around 20% weightage. And this weightage might change by 5% at the most during the course. So there are no particular course reference for this. You are expected to follow these lectures carefully and do the assignments diligently. But some of the resources that you can refer to are these. So I have mentioned 2 textbooks from Resavi. One is Design of CMOS Phase Lock Loop from Circuit Level to Architectural Level. The Kindle version of this is available. The other one is, of course, our Holy Grail, Design of Analog CMOS Integrated Circuits. There are also lectures by Dr. Saurabh Saxena from IIT Madras. These lectures are on phase lock loops and they are available online. So if you are interested to learn more, these are the 3 resources I would recommend. So any questions on the overall course or the grading or references? Okay, so then let's start with some basics. Okay, so we are first going to learn about the relationship between phase and frequency. Okay, let's say I have a signal given by y of t is equal to a naught cos of omega naught t plus phi naught. Okay, let's analyze each component in this signal. So a naught is called as the amplitude. This whole argument within cos, that is omega naught t plus phi naught, will be referred to as either the total phase or just phase. Okay, and this will be represented using the symbol phi. Now this is a function of t. Therefore, we'll show this as phi of t. Okay. Now let's look at omega naught. Omega naught is basically the angular frequency. And this is represented in, what is the units? Radians per second. And this is equal to 2 pi f naught, where f naught is represented in hertz. So you'll see that we use the same term frequency to represent both omega naught and f naught. Technically, omega naught is angular frequency, but this term frequency is usually interchangeably used for both omega naught and f naught. And this is done with the understanding that omega naught is represented in radians per second and f naught is in hertz. Okay. Now, this is also related to the time period of the signal, and that is given by 2 pi by t naught, where t naught is in seconds. Now, I'm sure most of you are familiar with these terms, but I want to establish all the notations in the beginning of the class. Okay. So this phi naught is called as, either initial phase or phase offset. Now, you might have seen that in some context, when they refer to phase, they are talking about the phi naught, right? But for this course, this is the notation we will follow. When we say phase, we mean the total phase, and this phi naught will be called as either initial phase or phase offset explicitly. Okay. So again, this is just a reminder. Whenever you see the term phase in an article, paper, or a textbook, please check the definition that they have used before you proceed. Okay, so this is clear. Then let me give you an exercise. So we have y of t equal to some a naught cos of omega naught t. There is no initial phase. You have to plot y of t, phi of t, and derivative with respect to time of phi of t. So why don't you give it a try? Okay, let's try this. So y of t is straightforward. The cosine waveform. So x-axis is time, y-axis is y of t, and we have the one period roughly here. So let's now look at phi of t. Again, x-axis is time, y-axis is phi of t. So what is the expression for phi of t? So this is omega naught t. This is equal to 2 pi by t naught into t. So at the instant t naught, what should be the value? It should be equal to 2 pi. At 2t naught, this will be equal to 4 pi. So this is an important result here. So for every time period, you have a phase accumulation of 2 pi. Okay. Now, what is the slope of this curve? 2 pi by t naught or omega naught. Okay. So now let's plot d phi by dt. So with respect to time, what do we get? It's a constant. What is its value? 2 pi by t naught or omega naught. Okay. So basically, when we differentiate the total phase, we get the instantaneous frequency of the system. Okay. In our case, the instantaneous frequency is constant throughout. Therefore, we got the value omega naught. So now let me ask you another question. Let's say I integrated and I calculated the area under this curve from T1 to T2. What does that value represent? What is the significance of this area? Total phase that has been accumulated. So let's look at this. So what we are doing is basically integral of d phi of t by dt from T1 to T2, right? This is basically phi of t from T1 to T2. So that gives you phi of T2 minus phi of T1. Or in other words, this is just the phase accumulated from T1 to T2. So if I were to mark this quantity onto this waveform, so I have T1 here and T2 here. So I'm basically looking at the phase that has been accumulated. So this quantity. Okay. All right. So now here is a homework for you to do. So now I'm giving you a y of t with some initial phase offset. So you have to repeat this exercise once more. You have to plot y of t, phi of t, and derivative of phi of t with respect to time. And do this and convince yourself that the results we have just explained are valid even in the presence of a phase offset. Okay, so let's do one more exercise. Now I'm taking my y of t as some sinusoidal waveform with some total phase. Okay, and I'm going to give you how this total phase is going to look like. So this is with respect to time. Let's say this is T1, 2 T1, 3 T1, and 4 T1. This is 6 pi. Okay, so you have to plot y of t. So let's look at the answer. So we see that there is a phase accumulation of 2 pi as you go from 0 to T1, which means within this time, you need to have one full period of a sine wave. So that gives you this. And this again repeats for the next cycle. So now after this instant, it takes the time between 2T1 to 4T1 for us to get a 2 pi accumulation. So that means now our clock, our sine wave is going to look like this, right? So what is, let's say what is the instantaneous frequency till 2T1? Let's say this is some omega 1. So omega 1 is 2 pi by T1. And if this is omega 2, what is the relationship between omega 1 and omega 2? It's half that. So omega 2 is basically omega 1 by 2. Is this clear? Okay. So now let us look at the relationship between phase and delay. So let me assume an ideal buffer. So we have this buffer which has a delay given by delta, right? So if I have some input in of t, let's say this output is out of t. So can you give me the expression for out of t in terms of in of t and delta? So this is going to be in of t minus delta. Okay. So now if I have in of t as some sine wave, my out of t is going to be a sine wave that is delayed by some delta. So this point is going to be delayed by a delta, right? So let me write the expression for in of t. Let's say this is some sine omega naught t. So can you write out of t and tell me the expression for the phase offset? My out of t is going to be sine of omega naught into t minus delta, right? So this is sine of omega naught t minus omega naught into delta. And this now I can compare with the expression we had earlier, sine of some frequency into time plus the initial phase offset. So this gives us that now the output signal has an initial phase of minus omega naught delta. This I can represent as minus 2 pi by t naught into delta. So if you have a delay in seconds, you can convert that into phase by scaling it with omega naught and then adding a negative sign. So the negative sign is coming because every time you delay the signal, you are actually reducing the total phase. So that is why the negative sign is coming. Okay, so now let me ask you another question. Given a single sine wave, we know now how to calculate a phase. What if the signal was a collection of sine waves, such as a square wave? Okay, so let's say our signal that we are now going to deal with is a square wave. Right now, if this is going from -1 to +1, and if this has a frequency given by omega naught, then I can write my in of t as a collection of sine waves based on Fourier series. So this is going to be sinusoids which are harmonics of omega naught t. And for a square wave going from -1 to +1, the Fourier coefficients will be 4 by n pi. And given the symmetry of this signal, we have to sum it up for odd ends, right? So now I again pass this signal through a buffer with a delay delta. Now this is my in of t. And for the output, I would expect to see a delayed version of the square wave. Now we are required to relate this delta to the phase of the signal. But given that this is a composite signal with multiple sinusoids, how would we go about doing this? Do you understand the problem? So turns out, for cases like these, that is where you have an absolute delay and you are delaying a signal in time domain, we still convert it into phase in terms of its fundamental frequency. So to explain this, let me represent this in of t, which is this complex function, which is this composite function, as some function gamma of omega naught t. Okay, then it becomes very clear. So my out of t is still equal to gamma of omega naught into t minus delta. So this gives you gamma of omega naught t plus some phi naught, where this phi naught is now minus omega naught delta. So when you deal with square waves and there is a delay involved, if you have to represent that into phase, you again rely on the fundamental frequency. So the phase offset is still equal to minus omega naught delta, which is equal to minus 2 pi by T naught into delta. So you will see that throughout this course, we use the term phase and delay very, very interchangeably because this is a very easy relationship to do. This is clear? Okay. So let's now move on to a little bit more complicated circuit. So we start with a delay line. Now I'm going to broadly classify the delay line into two categories. So the first category is what we call as a true time delay line. Okay, so let me explain what is meant by this. Let's say I have some signal like this, and we are required to delay the signal while maintaining the exact waveform shape. The amplitude information should be preserved as it is. Okay, then this is called as a true time delay line, a delay line which is able to delay the signal while preserving the exact shape of the waveform, while preserving all the information, is called as a true time delay line. Now, the second category is wherein we are interested in only delaying the edges. Okay, so let's say I have a clock waveform like this, and I'm interested in delaying these rising edges very, very accurately. So what I'm looking for is some output like this, where I know that these rising edges have been delayed by the same factor without introducing any error. Now, in these systems are usually immune to noise, even if the noise gets introduced in the stable high and low regions. So we don't want any noise introduced in this process, but if some noise gets introduced in the high or low regions, it usually doesn't affect the system performance. So this is a much more lenient delay line if you think about it. So a true time delay line is implemented using transmission lines. It can be implemented using delay lines consisting of inductors and capacitors. So this is called as LC delay lines. Or you can have active implementations using amplifiers. Now, these are basically all-pass filter implementations. Okay. Now, if you are interested to learn more about true time delay line, I recommend that you can look at Dr. Rimon's thesis. So this thesis has been uploaded onto his website, and you can read the first chapter of his thesis to get an idea. Now, in this course, we will not be dealing with true time delay lines. Our course is all about delay lines, which will delay the edges. Okay, so we have some leniency in designing these delay lines. Now, can you guess how we will implement such a delay line? I mean, what circuit component that you have learned that will allow me to delay the edges? Buffers, right? So you can take a CMOS inverter, put two of them together, you'll get a buffer that is going to delay the edges. So this sort of delay lines are generally implemented using CMOS inverters and different variations of CMOS inverters. Yeah, and this is usually used for delaying clock signals. Okay, so now we have to do a recap of CMOS inverters. So we'll quickly do a recap of CMOS inverters, establish notations related to rise time, fall time, propagation delays, etc., and calculate the delay. So a CMOS inverter consists of a PMOS and an NMOS connected in this fashion. This is the input, this is the output, and this is the symbol for a CMOS inverter. Now, if I give a rising edge at its input, what do I get? Falling edge, and vice versa. Now, if this is VDD and this is 0, What comments can you make about the inverter output? What would be the values corresponding to low and high? So this will be 0 and VDD. Okay. So now let me ask you a question. As you might have guessed, this course has a lot of, this is basically an analog course. Now, anytime we deal with an analog circuit, our general mode of analysis is to find a bias point and then see how we can apply small signal analysis around that bias point, right? So the question is this: can we use the same method of small signal analysis on the inverter when it is driving a clock signal? So is the question clear? Question is, can we use small signal analysis for the inverter when it is driving a clock signal or a signal as shown? I mean, the answer is either yes, no, under certain cases. So you can give it a go. I mean, wrong answers are also encouraged. Some answer is what I need. So you said input frequency, is it? Input signal. Huh. So does that everybody agrees with them, or do you have a different answer? But the question is valid, right? You're able to understand the question. So any other answers? So what if I choose my bias as VDD by 2 and then say I have a signal around it? So that is a key point. So small signal analysis is valid. Somebody else was saying something? Okay. Small signal analysis is valid when the signal we are applying is small compared to the bias point, right? So now we are engineers. We shouldn't be satisfied with the answer saying that it should be small. We should ask the question, how small is small enough? So if your transistor is biased in saturation region, in your analog class, you might have derived this condition. The small signal should be much, much smaller than twice of VGS minus VTH. Right? So this VGS is basically the gate to source bias voltage that you have applied. And this Vin is the incremental gate to source voltage that you are applying. And this is when your transistor is biased in saturation region. Right? So as long as this condition is satisfied, you can do small signal analysis. But in our case, our signals are swinging from 0 to VDD. They are swinging so large such that even the region of operation of the transistor is going to change. So we are in large signal analysis domain, and you cannot do small signal analysis when you are talking about a clock that is varying from 0 to VDD. Is this clear? Okay. So now let us calculate. So first let us establish the notations for TR and TF. So TR is basically the rise time of the signal. How do I measure this? So I have a signal edge like this. How do I calculate the rise time? %80 to 10% to 9. So you can mark the 10% of the total value. So if the signal is from 0 to VDD, this will be 10% of VDD to 90% of VDD. And then you look at the time taken by the signal to cover this range. So that gives you the rise time. Similarly, for the fall time, you again look at the 90% point and the 10% point. And this time will give you the fall time. Okay. Now, there is nothing wholly as such about this 90% and 10% numbers. In fact, in some cases, you will see that the 80% and the 20% points are used. And this is generally used if your signal, zero and ground are very noisy, and it becomes tricky to identify this transition. So again, look at the definition whenever you see the rise time and fall time expressions. And if nothing is mentioned, it is safe to assume 10 to 90%. Okay, good. Now let us look at propagation delays. So we have propagation delay from low to high and propagation delay from high to low. So can you tell me the definition for propagation delay from low to high? I mean, you've seen this. So tell me, what is the transition happening at the output? 0 to VDD, right? So if, let's say this is my input and this is my output. So I calculate the time at which it reaches the 50% of input. And we look at the time at which it reaches 50% of the output. And this gives you TP-LH. So the LH refers to low to high, and this transition is happening at the output. Okay. So similarly, let us do TP-HL. So my output has to go from high to low. So I look at the 50% of the input and the time at which it reaches 50% of the output. And this gives you TP-HL. Basically just revisiting all the definitions. Now, once you have TP-LH and TP-HL, you can tell the propagation delay of the inverter using a single number. That is, we simply take the average of both these. So as such, TP doesn't have a physical significance. It's just an average of two values. Therefore, the default approach, a good practice, is to report TP, TP-LH, and TP-HL when you are reporting the propagation delay for an inverter. Okay. So now let's look at how to calculate these parameters. We will take the simple case of calculating this for TP-LH. So we have the inverter. So I give a rising edge. I will get a falling edge at the output. Now I'm going to club all the capacitance at this output as some CL. So can you tell me what are the components that contribute to CL? Roughly, like what constitutes CL? Why do I have a capacitance there? The drain to bulk volt, CDB, I think. Yeah, CDB is what you mean, right? Yeah. So basically, the CDB of this NMOS, CDB of this PMOS. Similarly, the CGD of NMOS and PMOS can also be split into two capacitance, one at the output and one at the input. So I'm going to club all of this simply as self-capacitance. These capacitances are coming from the inverter itself, right? Anything else that can contribute to CL? Next stage. So input capacitance of the next stage. So you can think of this driving another inverter. Then the gate capacitance of the next stage will also contribute to CL, right? And we can also have parasitics associated with routing. So we have already done the calculations of each of these in E370 as well as in E619. So we'll not go into the details of those calculations here, right? And it's not required also. It's more important to understand generally from where these capacitances are coming from. Okay. So now our problem reduces to finding out how this capacitance is charging and discharging through these transistors. Once we find that out, we can write the expression for it and calculate the delay. But this is actually a very complicated and involving problem. So for example, I have right now drawn my input edge as a real edge consisting of a finite rise time. But if you have a finite rise time, we have to worry about when the NMOS is turning on, when the PMOS is turning on, and the strength with which it is turning on, right? The other part is the capacitance that we have written here, especially the self-capacitance and the input capacitance of the next stage. They are functions of the voltage here. So let me call this as VI, and this is V0. So the capacitance at this node is going to be a function of V0. Right? So nonlinear capacitance, that also complicates. So the one reason why we may want to do this complete mathematical analysis is for the pure joy of solving that mathematical equation, right? But other than that, if you want the exact value, run a simulation. We have very powerful simulation tools that can give you the result. Now, even if we derive the exact expression, as a designer, it may not be of much use to us because the equation is going to be so complicated that looking at it, we will not be able to make useful statements such as, oh, I decrease this parameter, I can reduce my delay. Or if this parameter increases, my delay will increase. So we will not be able to make such statements as well. So really there is not much reasons, not much motivation for us to do the whole complicated calculations. So we are going to make some simplifications so that we have equations that you can write on a piece of envelope and then do calculations. Okay. So the first assumption we are going to do is that our input has a step response. So at t equal to 0, it immediately jumps from 0 to VDD. Okay. So now for calculating the delay, we only have to find out the time it takes for the output signal to go from VDD to VDD by 2. Because the input goes from 0 to VDD by 2 instantaneously. So this is for calculation of high to low propagation delay, TPHL. Okay. Secondly, we will assume that during this region, when the output is going from VDD to VDD by 2, we are going to assume that the CL is a constant. So these two assumptions will make our life so much more easy. So now let's say this is happening at t equal to 0. Let us look at the states of this system at t equal to 0 plus. What is the value of input Vi? VDD, right? Output? VDD, because it is yet to start decreasing. Okay. So can you tell me what region the PMOS is in? So let's look at the PMOS. What is its VSG? 0. Its source voltage is VDD, gate voltage is VDD, so its VSG is 0. So what region is it? Cutoff. What about the NMOS? Okay, let's look at it. So what is its VGS? VGS is VDD. So now we have to find out the minimum value of 3 quantities, right? To find out the operating region of this NMOS. So the first quantity is VGS minus VTH, which is VDD minus VTH. What's the second quantity? VDS, which is V naught. The drain to source voltage is the output voltage. And finally, VD sat n. So now clearly, so what is my V naught value at, this is also VDD. So you can expect that the minimum value is either going to be VDD minus VTH or VD sat n. So now in the digital courses, E370 as well as in E619, we usually make the assumption that this is a short channel transistor. Therefore, VD sat n is expected to be a smaller value, and we say this is in velocity saturation, right? Now, that is a very valid assumption for a digital circuit, because given the current trends in semiconductor industry, you are very, very less likely to see a long channel transistor in a digital circuit. Whereas in analog circuit, you will encounter both long channel transistors as well as short channel transistors. So anyways, you are familiar with the calculations, including the short channel transistors. So let's give it a try with a long channel transistor. So we are going to assume that transistors are long channel transistors. So whatever method I use for calculating the delay using this long channel transistor assumption, you can follow the same method for deriving the delay if it was a short channel transistor. So the method remains the same, but let's try with long channel transistors. So now what is the region of NMOS? What saturation? Pinch of saturation. Okay. So what is the current through the NMOS during pinch of saturation? Half mu n COX W by L into VGS minus VTH the whole square into 1 plus lambda VDS, right? So now my problem has reduced down to this. So I have a PMOS that is on. Then I have some current, IDS, which is pulling out the charge from a capacitor CL. I could also model this in the following fashion. I have some capacitor CL, and I can model this NMOS transistor as some equivalent or effective resistance. And then we can talk about discharging this capacitor using the effective resistance, right? And this is what we usually do for digital circuits. Why? I mean, both of these are going to give you the correct results. So why did we prefer the second method over the first in digital circuits? Sorry? That is true, but I can use the exact equation for the current and then solve this. Yeah, so this gives you a first order RC equation, which is easier to solve. But more importantly, when you have a large digital circuit, you can reduce this whole thing into an RC circuit. Okay. And then we use Elmore delay model, make a first order time constant approximation, and then you can quickly calculate the delay. So that was one major reason why we did this method in the digital circuit course. Now here we are going to be dealing with circuits that are much smaller in size in terms of the instances when we want to calculate the delay. And also, if we model this as a current directly, it makes it easier to do noise analysis at a later stage. Okay, so we are going to model this as a current and then calculate the delay. So let me quickly sketch out the current waveform. So as I'm varying my VDS, which is in our case the V naught, my IDS is going to look like this. What is this point now? This will be VDD minus VTN. And our current, we are going to solve this for the current going from VDD till VDD by 2. Okay. So can you calculate what TPLH is? So you can start from this point. The current through the capacitor is equal to CL into dV by dt. Therefore, dt is equal to CL by IC into dV. So I have to integrate this from 0 to TPLH. And what integration limits do I have here? So this goes from VDD to VDD by 2 into CL by IC. So this equation, for ease of analysis, I'm going to simplify this as a part that doesn't depend on VDS or our V0 into 1 plus lambda V0. Okay. So now I can write this as VDD to VDD by 2 into CL by I0 into 1 plus lambda V0 into dV0. Is this equation correct? I have made a small mistake here. Can you tell me what that mistake is? Our effective will not be in the picture because we are going with this model. So you can calculate the delay either using an effective resistance and the capacitance or as the current that is being pulled out of CL. So why is the negative sign coming? Correct. So our equation, so this equation assumes that there is a current flowing into the capacitance. Yes, I have replaced it with the equation for the current through the NMOS. So I need to have a negative sign. So can you solve this? You can use the binomial expansion to bring 1 plus lambda V0 onto the numerator. So I will use the negative sign to change the limits. VDD by 2 to VDD. CL and I0 are constants. They come out of the integral. Then you have 1 by 1 plus lambda V0 into dV0. So this gives you CL by I0 with the same integral limits. This 1 plus lambda V0, I can write it as 1 minus lambda V0. This is assuming that lambda V0 is a small number. Lambda is typically very small, so it's a valid assumption. And then this is a straightforward integral. What answer do you get? So we have CL by I0 into the first term will give you VDD by 2 minus the second term is V0 square by 2, and then you put these two limits. So this should give you 3 by 4 into VDD square. So let me take VDD by 2 outside, and the expression I have is CL by I0 into VDD by 2 into 1 minus lambda 3 by 4 into VDD. Everybody got the same expression? Okay. So now the moment you calculate an equation like this, the first step is to do some sanity checks on it to see if this expression is making sense. What is the first sanity check that you can apply? This is true for any equation that you derive. You immediately check for its dimensions. What is the dimension of the LHS? This is TPHL, right? So what is the dimension of LHS? This is in time. or in seconds, units. Now, can you calculate the dimensions for the RHS? That is also time. Yeah. So this parameter is dimensionless. This is dimensionless. You have CL. So CL, you can think of it as some charge by voltage, where in the charge, you can think of it as some current into time. So that into it's VDD by I naught. So basically V by I. So that will also give you the dimension as time. Okay. The second check that you can do is to see if there is any parameter that you can make as 0 or infinity, and then see if the answers are matching, right? For example, in this, let's assume that the transistor have no channel length modulation, right? That is, if the lambda is equal to 0, then our curve is going to be flat here. And this value will be some I naught, correct? So if lambda is equal to 0, our problem simply reduces to a constant current source, I naught, pulling charge from a capacitance. And this is very straightforward to calculate, right? So you can calculate what the TPHL for this is. Okay, can you tell me what the answer is? So this will be CL by I naught into delta V, which is VDD by. So you can use the same current equation and then quickly calculate. Okay. So now you put lambda equal to 0 in the derived equation. What do you get? The same expression, right? So these are some of the ways in which you can cross-check your answers. So now let's analyze the equation that we have got. So let me copy this. So what are the circuit inductions we can get from this circuit? That's what get from this equation. So that is what we are interested in. So let's say I increase my CL. What happens? Delay will increase. And this is expected, right? If you increase the capacitance associated with a node, it will take longer time for that node to charge or discharge. So you can expect the delays to increase. Now, let me also replace the I naught with its equation. So this is mu n COX W by L. So it's half mu n COX. That half cancels here. This into VGS, which is VDD minus VTH the whole square. Okay, we have the full expression here. So next, what happens if I increase my VDD? So let me take this VDD out of the square bracket. So I'll have CL VDD by the whole mu n COX W by L expression. Then I'll have VDD square outside the bracket. 1 minus VTH by VDD the whole square into 1 minus 3 by 4 into lambda VDD. So then I can cancel this VDD square and this expression. Okay. So now looking at this, can you comment on what happens when I increase the VDD? Let's look at each of the terms. So this VDD increases. VDD increases. This factor is going to decrease. Now it's 1 minus a smaller factor. Therefore, this whole factor is actually increasing. What about the numerator? This is going to decrease. So overall, my numerator is decreasing. My denominator is increasing. Therefore, if VDD increases, my delay is going to reduce. Okay. What happens if I increase W by L? So it looks like it is going to decrease, but there is a catch here. Yeah. So if I reduce the W by L, so we talked about the self-capacitance here, right? The self-capacitance is actually proportional to W into L. So if I increase the W to increase the W by L, so initially you might see an advantage, because even though the capacitance is, you will see an advantage, especially if the capacitance is dominated by other values. So your self-capacitance is increasing slightly, but your overall capacitance is not changing much because it could be dominated by other factors. But as you keep increasing the W by L, eventually you'll reach a point where the self-capacitance is a dominating factor. And beyond that point, you will not see any improvement in the delay. So this is actually a trick question. It depends on the self-capacitance value. Okay. So far in this class, we have seen why we should be learning about the time domain circuits. Then we saw the basics of phase and frequency, phase and delay. And then we have started discussing about the delay lines with a quick recap to the inverter details. So please feel free to go and look up your inverter basics. We'll continue the class on Wednesday.